Hello everyone. Now we will have a tutorial session and we will solve some numerical problems on the basis of discussion we have made in last 4 classes. Our first problem statement is a distillery unit producing 180 TPD alcohol generates 42.9 meter cube per hour MEE condensate, that is multi effect evaporator condensate, and 3.75 meter cube per hour cooling tower blowdown. Determine critical dimension of the secondary clarifier and multigrade or carbon filter. Also determine the oxygen requirement in the aeration tank. Assume the inlet BOD of the aeration tank is 130 ppm and the aeration is done by using diffuser. The HRT and surface loading rate for the secondary clarifier are 5 hour and less than 18 meter per day, that is meter cube per meter square per day. The HRT of the filter unit is 6 minute and the L by D ratio is 0.8. So, now we have to solve this problem and we know that this problem is basically based on the treatment of wastewater in a distillery unit, and in this case as ME condensate is there, that means thermal process is used for the condensation of spent wash, and we see the flow sheet for the water treatment. So, we have ME condensate. So, this condensate is coming into the equalization tank and then equalization tank to conditioning tank. So, here pH adjustment takes place and then it is going to ICX, that is biological tower. So, here anaerobic condition prevails and biogas is produced and the gas is lost, it is flared. Through the flaring the gas is burned and the water which is coming out from ICX goes to aeration tank, and in aeration tank oxygen is supplied, microbial seeds are provided and remaining organic compound present in the water is degraded here. So, we have to calculate the oxygen requirement in this tank, and after this the treated water goes to secondary clarifier and the water enters into the HRSCC and the sludge goes for dewatering into a decanter, and another water stream that is provided in the problem statement, that is cooling tower blowdown. So, that directly does not enter into the equalization tank, it enters here with the treated water after secondary clarifier and then in the HRSCC both streams are added. So, here HRSCC we are getting another settling. So, the clarified liquid is passed through the tertiary treatment unit. So, this is our MGF and ACF multigrade filter and activated carbon filter, then it goes to UF, RO, UV and then used in the plant. So, we have to find out the dimension of this ACF and MGF, we have to find out the dimension of this SC secondary clarifier, and we also have to calculate the oxygen requirement in this aeration tank. So, these are the task we need to complete. Now, you see in distillery ETP the ME condensate is treated through the condensate polishing unit, through equalization tank, anaerobic digester, aerobic tank followed by tertiary treatment. However, the cooling tower blowdown is treated only through tertiary unit. Thus, if we assume that there is no loss of water during the process and ignore the sludge volume, only condensate water will be processed in secondary clarifier. However, both condensate and blowdown water will be used in multigrade and carbon filter. Now, we have taken one assumption that we are assuming that the sludge volume is negligible. So, although there will be some sludge production, but by this assumption the design will be more conservative, so there will be no harm. Now, since the HRT of the secondary clarifier is 5 hour, the working volume of the secondary clarifier will be 5 into 42.9 equal to 214.5 KL. Why so? Because you see here this condensate is coming and we are assuming there is no loss of water. So, all condensate water is coming to SC secondary clarifier. It has certain flow rate, that is Q meter cube per hour, and then it have some retention time that is 5 hour. So, total volume of the SC will be 5 into 42.9, that is equal to 214.5 kiloliter or meter cube. Now, since the surface loading rate is 18 meter cube per meter square per day, so that is equal to 0.75 meter cube per meter square per hour. That means, the conversion from day to hour. So, we have to divide 18 by 24. So, that is coming 0.75 meter cube per meter square per hour, or that is equal to 0.75 meter per hour. So, we have to calculate the cross sectional area, and that cross sectional area can be calculated by this relationship. Say this is the clarifier. So, water is getting out from this after the settling, and the water will be having inside the clarifier a upward velocity. Okay, so, that will be having a upward velocity. So, that is a V. Okay. And now, we have a cross sectional area. So, that is A. So, A into V, that is equal to nothing but Q. So, we have to calculate the value of A. So, A is equal to Q by V. So, Q in this case is 42.9 meter cube per hour, or say 42.9 kiloliter per hour, and here we are getting that V is equal to 0.75 meter per hour. So, the area is coming as 52.2 meter square. So, if we get the value of area, then we can get the diameter. Another thing, we can also calculate the height, because we have the volume, we have calculated the volume is 214.5. So, here if the total volume V is equal to 214.5 KL and the area is your 57.2 meter square. So, height if we consider as L, so that or H, so that height is equal to this volume divided by this area. So, we can calculate this divided by this area. So, we are getting this equal to 3.75 meter, but this is the working volume basically. So, the height corresponding to the working volume of the reactor basically. So, in real case we need to keep some freeboard. So, in this case minimum 0.3 meter freeboard is necessary. So, height will be 3.75 plus 0.3. So, that is 4.05 meter. So, 4.05 meter will be the actual height of the secondary clarifier. So, actual volume will be this 4.05 into the cross sectional area, that is 57.2. So, that is equal to 231.7 meter cube. We have considered that cylindrical part, there will be some assumption. So, that way we are getting this one. Okay. The radius of the secondary clarifier will be how much? Then we need to calculate the radius. So, this is our area. So, A is equal to pi r square, or r is equal to root of A by pi. So, this is root of A by pi. So, that is 4.27 meter, that is the radius, and so the diameter will be 2 into 4.27, that is 8.54 meter. So, now we are able to find out the height and the diameter of the secondary clarifier. So, one problem is solved. Now, in the second case we have to find out the dimension of the filter units. We have to find out the dimension of the filter unit. So, in this case it is a unit of tertiary treatment. So, both condensate and the blow down water will be passing through it. So, the total volume of water that will pass through it, that is equal to 42.9 plus 3.75 meter cube, that is 46.75 meter cube per hour basically. Okay. So, the volume of water processed in 6 minutes, it is given it in 6 minutes. volume of water processed in 6 minutes, because 6 minutes is retention time. So, 46.65 per hour, so divided by 60 into 6. So, that is equal to 4.67 meter cube in 6 minutes. So, this is the volume basically. We have two filter units. So, one getting entry, then it is out, it is entry and that is out, and here it is maintained that 6 minutes each. So, that 6 minutes each, then 4.67 meter cube flow is going there through this, and now we are assuming that these two tanks are having same dimension and assuming diameter as x and length is equal to 0.8 x, because L by D is equal to 0.8, it is given in the statement. So, our this assumption is okay, length is equal to 0.8 x and diameter is equal to x. So, then what will be the volume? Volume is equal to pi d square by 4 into h. So, that is equal to x square by 4 and this h is equal to 0.8 into x. So, then this equal to volume equal to how much? This is 4.67. We have taken some approximation, this bottom part we have ignored basically, with some assumption this is applicable, and then from this expression if we get, so by simplification this 0.628 x cube equal to 4.67 or x cube equal to 4.67 divided by 0.628, that is equal to 7.44 or x equal to 1.95 meter. So, x is equal to 1.95 meter. So, that is the diameter, and then the length will be 1.95 into 0.8. So, 1.56 meter. So, now we are able to find out the dimension of each filter unit. Next part, we have to find out the air requirement in the aeration chamber. So, in the aeration chamber we have seen that the wastewater after treatment in the bio tower, it enters into the aeration chamber. So, your BOD value is very less. So, 130 ppm BOD is coming, and we can assume that it is treated and 30 ppm BOD is permissible in the treated water. So, the removal is equal to 130, that is 130 minus 30. So, that is equal to 100 ppm. So, that is the removal of BOD. Now, since the aeration is done by using diffuser, the air requirement may be considered as 36 meter cube per kg of BOD removed. This value we are assuming, this is given in some reference. So, that is assumed, and if you assume, then the in this case only the condensate water is treated in this aeration unit, not the blow down water. So, the volume is treated water volume is 42.9 in this unit, and here the removed BOD is 100 ppm, that is equal to 0.1 gram per liter or 0.1 kilogram per kiloliter or meter cube. So, this value we will be multiplying now 42.9 meter cube into 0.1 kg. So, 4.3 kg we are getting per hour it is produced. So, air requirement will be how much? This 36 into 4.3, because we have taken this assumption. So, that 155 meter cube per hour air will be required. Now, we are able to solve the problem completely. Now, we will see the problem number 2. Statement is, in an industrial biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 10% of solid food grains. The elemental composition of the waste food grains on dry basis is carbon 52%, hydrogen 9%, oxygen 29%, nitrogen 10% on mass basis. Around 85% of the waste food grains are converted to biogas, and all the converted hydrogen forms methane. If the flow rate of the slurry is 4000 liter per day, calculate the rate of biogas, that is CO2 plus CH4 production. So, this is another anaerobic digestion problem, another problem related to anaerobic digestion, and we have to calculate the rate of biogas production. Okay. So, the composition is given and the CHNS or elemental analysis is also given. Now, we will have flow rate of the slurry as 4000 liter and dry solid of waste food grains is given, that is 10%. So, what is the dry solid of waste food grains used in this case in this 4000 liter? So, 4000 into 0.1010%, 400 liter, and we are taking some assumptions here that slurry is having the density is 1 kg per liter, then only it will be 400 kg. So, we have taken some assumption. Now, we will see how much carbon is present in 400 kg of this dry food grains. So, here carbon is equal to say 52%. So, 400 into 0.52, that is 208 kg, and hydrogen is say 9%. So, 400 into 0.09 that is equal to 36 kg, and oxygen 400 into 0.29 because 29%. So, 116 kg, and nitrogen 10%. So, 400 into 0.1, so that is equal to 40 kg. So, these are the different amount of carbon, hydrogen, oxygen and nitrogen present in the feed. Since 85% of the food grains are converted to biogas. So, carbon converted to biogas will be 0.85 into 208 kg, that is equal to 176.8 kg. Hydrogen converted to biogas will be 0.85 into 36, that is equal to 30.6 kg. So, here another condition is given that all hydrogen is converted to methane. Since all the hydrogen is converted to methane, the methane production will be how much? So, CH4 if we say, so that is 12 plus 4, that is equal to 16. Okay. So, 12 gram carbon gives 16 gram methane and 4 gram hydrogen gives 16 gram methane. So, 16 by 4 into 30.6 kg, that will be the methane production, that is 122.4 kg, that is equal to 7.65 kilomole, because now we will divide this divided by this the molecular weight of methane, that is 12 plus 4, that is 16 again. So, we will divide it by 16 and we will get it 7.65 kilomole. And now, carbon used for methane production equal to how much then? So, we are having 122.4 kg of methane. So, what is the carbon production? 12 gram gives 16 gram. So, 12 by 16 into 122.4 kg, that is equal to 91.8 kg. So, this is the carbon used for the methane production. So, what is the rest carbon? Carbon that is used for carbon dioxide production, that is the total carbon 176.8 minus this 91.8. So, that is we are getting 85 kg, and carbon dioxide produced equal to how much? C plus O2 or then CH4, CH4 will give us CO2 plus H2O plus oxygen. Okay. So, carbon dioxide produced equal to how much? It is having say 1 mole will give 1 mole. Okay. So, CH4 plus 2O2, CO2 plus 2H2O. So, in this case 1 mole methane gives 1 mole carbon dioxide. So, that is 12 plus 32, 44 and here 16. So, that is why we are getting CO2 produced, that is equal to 44 by 12 gram carbon. So, 12 gram carbon will give us 44 gram of CO2. So, that 44 by 12 into 85 kg of this carbon used for the carbon dioxide production. So, that way 311.66 kg CO2 will be produced, and then we will divide it 311.66 by this 44 and we will giving 7.08 kilomole. So, CH4 plus CO2 in the biogas, the CH4 we are getting 122.4 kg and the CO2 we are getting CH4 we are getting 122.4 kg and CO2 we are getting 3116.66 kg. So, that is equal to 434.06 kg or in terms of kilomole. So, that is 7.65 kilomole for methane and 7.08 kilomole for carbon dioxide. So, 14.73 kilomole gases will be present in the produced biogas. Now, problem number 3 statement is, if the average heat rate of a cogen power plant is 2611 kilocalorie per kilowatt hour, calculate the average efficiency of the plant. So, we have discussed in our previous class also that thermal efficiency is equal to energy generated into time divided by MC into CV into 100. So, this is the formula where MC is the quantity of fuel or feed consumed and Cv is the calorific value of the feed. So, this is the efficiency we know. So, now this efficiency we can write 100 divided by MC into Cv divided by energy generated into time. So, this one, and this term is nothing but heat energy input supplied by the fuel, the first term, to the power plant for a period kilocalorie divided by energy generated for the period, that is in kilowatt hour. This is electrical energy and this is heat energy. So, this ratio is which we are getting by this term. So, this is called heat rate. So, that heat rate in this unit kilocalorie per kilowatt hour. Now, if we want to get it in percentage, so then we have to take a factor for the conversion of unit from kilocalorie to kilowatt hour. So, that is equal to 859.8456 kilocalorie. So, this will be 100 into 859.8456 divided by heat rate. Now, we will be putting the heat rate in the same unit kilocalorie by kilowatt hour, which is given in this case. So, in our case here we are getting 100 into 859 into 8456 divided by 2611, and that which efficiency we are getting, that will be in percentage. So, the 33% thermal efficiency we are getting. Next, problem number 4. The statement is the flow rate of chrome bearing wastewater from a tannery unit is 2 kiloliter per day, contains chromium concentration or CH3 plus of 20 mg per liter. The efficiency of chromium recovery unit is 95%. Then calculate the amount of fresh chromium sulphate required per day. So, this is a problem related to chromium recovery in a tannery unit. So, chromium concentration in the wastewater is 20 mg per liter, it is given, and efficiency of the chromium removal is 95%. So, amount of chromium recovered is 0.95 into 20 into 2000 mg per day, because 2 kiloliter per day is our flow rate. So, that is that volume, and in liter 2000 and this 20 mg per liter. So, this unit is coming. So, 3800 mg per day, that is 38 gram per day. So, this is the amount of chromium recovered, and amount of chromium lost equal to how much? 1 minus 0.95 into 20 into 2000 mg per day, that is equal to 2000 mg per day or 2 gram per day, that is the lost. Now, this is chromium 3. Now, we know that 392 gram chromium sulphate. So, Cr2 SO4 whole 3, the molecular weight will be 392. So, here chromium is present as 2 into 52, that is equal to 104. So, 392 chromium sulphate contains 104 gram chromium. So, amount of fresh chromium sulphate required is equal to 392 divided by 104 into 2 gram chromium, which is lost. So, that is coming as 7.5 gram per day. So, this much of chromium is being lost, and that has to be fresh addition. So, now we are able to solve the problem, and next we are coming to problem number 5, and the statement is the flow rate of wastewater from a tannery industry is 2 kiloliter per day, and it has chromium content of 15 mg per liter. As per CPCB standard, the effluent should not contain total chromium as more than 2 mg per liter. Find the rate of chromium removal in gram per day required in ETP. If 90% of this chromium is recovered, how much MgO will be required for this recovery of the chromium if stoichiometric conversion takes place. So, here we will see that how much chromium is removed. So, that chromium removal may be taking place at the chromium recovery unit or in the effluent treatment plant. We are assuming this, that some part is recovered and some part is being removed in the treatment unit. So, influent chromium concentration 50 mg per liter and effluent concentration 2 mg per liter, because permissible limit we are assuming that it is the 2 mg per liter, and then flow rate of influent wastewater 2 kiloliter per day, it is given. So, rate of chromium removal, that will be 15 minus 2, that is removed, into 2 into 1000 mg per day, that is 13 into 2000 mg per day, that is 26 gram per day. So, this much of chromium is removed. Now, we are considering that 90% is recovered out of it. So, 26 into 0.9, so 23.4 gram per day, this is recovered, and for the recovered, what will be the chromium sulphate, corresponding weight of chromium sulphate recovered, that is 23.4 into 392 by 104. So, that is equal to 88.2 gram per day. And what are the stoichiometric reactions in this case for the chromium recovery? We know that this chromium sulphate which is used for the tanning purpose. So, that is present in Cr3 plus state, okay, that reacts with the MgO and H2O to give magnesium sulphate and chromium hydroxide, and that this is precipitated, okay, and again it is reacted with H2SO4 and gives Cr2 SO4 whole 3. So, at very high pH, that is pH 11, in this case pH 11 or more than that. So, then it gives this one. So, this precipitation we get. So, here the stoichiometry you see 3 into 40 gram molecular weight of MgO, and here 2 into 103 CrOH whole 3 is produced. So, MgO requirement will be how much? So, 3 into 40, this much of MgO is required for our 392 chromium sulphate neutralization, and then for 88.2 gram Cr2SO4 which is recovered. So, how much MgO was used? So, 3 into 40 divided by 392 into 88.2. So, that is equal to 27 gram per day. So, now we are able to solve this problem also. So, we have solved all the problems in this tutorial class, and we have seen that different industries produces different types of pollutants in the wastewater streams. Now, we will show you one video that will give the working of a sugar industry, and I hope you will enjoy it, and it will give you more clarification. The video is self explanatory. Please watch the video. Now, I think the video has made many clarity on your thoughts, and after this in this class, thank you very much for your patience.